Hello, everyone. So it looks like it's 10 o'clock now, and I'd like to start off by introducing myself. My name is Wyatt Pena, and I am a project manager here at Ridgetop Group. And I would like to thank everybody for joining us for today's webinar. Today's presentation will be covered by distinguished engineer James Hoffmeister, who most of us know as Hoffy. Hoffy joined Ridgetop, I believe, in 2003, but prior to that, he led a very successful career at IBM. And Hoffy serves on the board of directors for the Society of Machinery Failure Prevention Technology, MFPT, and was recently elected a fellow of that particular society. Without taking up any more time, I would like to start today's presentation, but I do want to ask everyone that they mute their mics during the presentation and save their questions until the end. So thank you everybody for joining us, and we will begin.
Good morning. This seminar is on Prognostic Health Monitoring, or PHM. Most of you might know PHM to be Prognostic Health Management, but we here at Ridgetop, we are aware of health management, but we primarily focus on the monitoring aspect, because management, that is the reallocation of resources, the shutting down of resources, etc., is really application or enterprise specific. It's not something that we could do as a general purpose solution. So with that, if you will, Wyatt, let's go to the next slide. Today, we're going to cover the Phm overview from a framework point of view. And we'll talk about the sensor framework, which is basically processes condition-based data. The sampling extracts feature data. Then there's two other frameworks, so we call it a two-stage multivariate core. One is a data processing framework, and the other is the prediction framework. Those two frameworks basically process the data, do some transforms, and produce prognostic information, remaining useful life, state of health, prognostic horizon. Then we'll talk about some example results. Next. There are many ways to look at prognostic health management. One is a prognostic block diagram, and you'll see that, for example, in 2 or 3 of the PHM societies, and they talk about data acquisition. I group that into the sensors framework. They talk about a feature vector or data processing framework, then a prognosis framework, which does all the prediction, and then a reasoning, which is fault identification, isolation, alerts, and of course your management. And the IEEE Society, for example, and the standards group that's being worked on, they've assigned various symbols to these various processes. The next slide shows a different view of a prognostic health monitoring or management. It's from the other one was like a block diagram or processing. This shows more or less of the data and the control flow. You have a node in the system to which a sensor is attached. That sensor and the intelligent firmware associated with that sensor collects data from the node, extracts the feature, and sends it off and gets routed to a feature vector framework or data processing that processes the data to convert it into an input that's acceptable to a prediction framework that actually does the prognosis of state of health, remaining useful life. pH is prognostic horizon. Then you have a different framework that's not it's more of a offline type of work. It's a performance validation. You really can't evaluate the performance of a prognostic node, if you will, until you've reached end of life, because you have to want to say, how accurate was I to the actual end of life? So until you get there, you really can't do performance validation. Then there's a framework that we here at Ridgetop, we're happy to help people with. We understand it, but it is really a customer-specific solution, and that's the fault management. Next. Okay, condition-based data. Condition-based data sounds good. We've heard about it. You do condition-based data as opposed to case usage or lifetime or some other kind of aspect to do prognosis. And it sounds very good, except that condition-based data is noisy. I mean, very, very noisy. You'll see that, for example, up there on the upper right corner is the output of a power supply. And you can see it consists of all kinds of signals. There is the DC voltage, there's some ripple voltage there, there's some shot noise, there's some thermal noise, and there's some ringing responses. There's all kinds of data. The data, everything can be used if you really think about it for prognostics. But you can't look at everything and you can't process everything. So a prognostic engineer has to look at the data, look at the failure mode of interest, look at the tools he has, the sensors he has, the processing firmware he has, and says, okay, this is the feature I'm going to look at. For example, ringing response. Whenever you impulse or perturb a power supply, that power supply tends to ring. And the ringing response that's a feature, that's a useful feature. But that ringing response also contains other features: amplitude, decay, and resonant frequency. So the feature data itself can also be very noisy. Next. Examples of measurement values that change: voltage, current, temperature, etc. And everything, practically anything you can think of, can be used for prognostics. Next. So anything that can be measured, calculated, derived is either noise or feature. Noise, in my world, is anything that you can measure or monitor that does not change in correlation to a particular failure mode of interest. Next. The sensor framework, as I mentioned before, is a sensor. It attaches to a noise. It samples the signal at the noise or condition-based data. It conditions that data to filter out noise, to mitigate noise, and to isolate and extract featured data of interest. Next. So, that seems very simple. Attach a sensor to noise, collect data, and process the data. Well, it's not quite that simple, because you have to take in consideration the sampling rate, the resolution, and the precision. For example, supposing the customer says, I want to detect failure at least 72 hours in advance, and I want the prediction estimate to be plus or minus 1 hour, and I want 10% accuracy. Well, okay, 72 hours plus or minus 1 hour, 10% accuracy. Okay, you decide that you're going to look at the ringing response, and the resonant frequency is, without degradation, is 2 megahertz. And when you do the physical failure analysis and the failure mode effects analysis, you discover that there's a 70% change. There's a change in frequency as you lose capacitance. Next. So, plus or minus 1 hour precision with 10% accuracy. Well, Nyquist criteria says that you need to sample twice per hour. And if it's 10% accuracy, then you need to do 10 samples per hour. So you're plus or minus 2, so now that totals down to 20 samples per hour. Means a sampling period of 3 minutes. But now you have to sync your sampling to when there's a perturbation in the power supply. Well, you don't really know when the power supply is going to be perturbed. So what you need to do is design your sensor so that just before you sample it, you actually inject a perturbation into the power supply. So that's a design consideration that most engineers won't think of unless they're a real prognostic engineer. Next. Okay, resonant frequency at 20 megahertz. Nyquist criteria then says, okay, now I got to sample at 20 megasamples per second. 10% accuracy, well, now I got to sample at least 400 megasamples per second. So I'm going to continuously sample at 400 megasamples per second for 180 days continuously. No, not going to work. You're not going to be up 180 days. Your system's going to go up and down. It's going to crash. You're going to have to start and restart. And furthermore, 6,000 trillion samples. Totally impractical. Next. Okay, so there's a way to do it. And it basically is you have a slow sampling rate. And when you sample at a high frequency burst mode. For example, TP, that's your period of time between samples, in our case was 3 minutes. You say, wow, now I got to sample every 3 minutes. Well, does that 10% really apply to the plus or minus 1 hour? If it doesn't, then you can say I can really sample at once every 30 minutes. That's a little bit more reasonable. Burst frequency, though, we really need to sample at 400 megahertz. Well, wait a minute. If I'm going to sample 400 megahertz for some period, my ADC, my analog to digital converter, has also got to be able to be process data at that rate. So in other words, it would do me no good to sample a node at a burst mode of 400 megahertz using a 1 megahertz ADC. It's inconsistent. It's not going to work. Next. So the output from the sensor, well, let me finish on here. So we've seen and we've discussed that sensing is more than simply attaching a sensor. You got to do noise filter, you have to do signal perturbation, you have to do sampling rate, you have to do burst mode sampling, you have to signal condition, you have to do analog to digital conversion, then that involves digital signal processing, domain transforms, and possibly data transforms. So there's a lot to sensing, the framework, sensing framework, than simply attaching a sensor to a node. It has to be designed. Okay. The signal now goes over to your data processing framework or the vector framework. And what you want is, when you look at it, feature data. If you've selected the right feature using FEMA and physical failure, it will form a curve. And that curve will change in direct correlation to the failure mode. If it doesn't change in correlation to failure mode, then you shouldn't be looking at that particular feature because it's noise. But feature data, even if you select the right one, it's noisy. It's curvilinear, it's got amplitude units of measure, and it's got a threshold variation. And if you try to attempt to use feature data directly, that means you need a model for every single instantiation of your sensor. Oh my goodness. That's not going to work. Because if I got 10 power supplies, even though they're the same power supplies, I've got 10 sensors, each power supply will have a different threshold. So you need a model for each power supply. No, that simply won't work, impractical. Next. Okay. So the feature vector framework has got to condition data. It's got to do some normalization. It's got to undimension the data, and I'll talk about that. It's got to do some transforms. The transformer is to go from feature data to what we call fault to failure progression signature. Then we're going to transform the fault to failure progression signature to a degradation progression signature, and then we're going to transform that to a functional failure signature. Next. Okay, now this is ideal data, and I'm using ideal data here primarily just to test out the software and also demonstration purposes. Ideal means it's noiseless. There's no noise to it. And you can see that it's a nice, perfect curve. That curve, when you think about it, failure is related to something that's changing. A capacitor, a resistor, transmission power. Something is changing. The elasticity, whatever it is that you're looking at, it changes. And it changes according to the laws of physics. And when you look at that, the physical model, the equation for it, it never changes. So it's got a characteristic curve. What we really want to do is convert that curvilinear data to a linear change. Now, because now that's application independent. And that's what the purpose that what we do when we change condition-based data to feature data, which is on the left, to functional failure signature, which is on the right. Next. Okay, noise issues. Noise is the problem. You have to address the noise any way you can. And we don't mean get rid of the noise totally 100%. You can't do that. It's too expensive. But you need to reduce the noise to a level at which you're able to meet the requirements, the accuracy requirements, time to detect the problem, and the accuracy to detect when it's going to fail. So when we say address noise, reduce it or mitigate it, we don't mean 100%. Enough to meet requirements. Next. Okay, there are many ways to do that. You can filter it, low pass, high pass, band pass. You can dampen the noise. You can clip it. You can comp it. You can do comment. There's thousands upon thousands of ways to filter or mitigate noise. You, as the prognostic engineer, the designer, it's up to you to figure out how to do that. You can also employ signal shaping techniques. You can also do data and domain transforms, FFT to IFT, etc. You can do fusion of resistance and voltage and current to calculate resistance. You can do data smoothing. There are many, many ways to do it. Your goal as a prognostic engineer or designer is to figure out what you can do to meet requirements at the least amount of cost and yet meet your accuracy requirements. Next. Okay, this is an example of features of failure analysis and FEMA. So suppose you have a sensor and you're looking at the ringing response and you decide that you want to look at the resonant frequency because the change in resonant frequency is directly related to a change in capacitance, which is a frequent or common failure mode in power supplies. So you have a signal model, you start with that. You can look at that and say, well, okay, I've got all kinds of terms in there. I've got an exponential decay, I got DC, I got small signal, I've got a sinusoid, which is my resonant frequency, and you can see that there's omega naught, and omega naught is a function of the LC of the power supply. And you've also got the quality of the circuit. And so your measurable frequency is as shown in equation 4. And therefore, if you have a high enough a Q, you can extract out the L and say that really the frequency change that I'm going to look at, assuming that the inductance doesn't change, is due to a change in capacitance. And though you can then say end up with equation 5. Next. Now, if you replace the original capacitance with P for the parameter and the change in P with dP, you can say, oh, that's P and a dP. And the feature data equals the feature data naught times this equation. So I can solve that in terms of P and dP. And that's what we've done here. And when I do that, when I take all these equations and I do that, I come up with what I call hello, is someone talking? A fault to failure progression signature. And it looks like that. Now, when we do that, next, I end up with this example, okay? My feature data is 10 kilohertz plus or minus 1 kilohertz. So my noise maximum is 2 kilohertz. So I want to get rid of that noise. Well, one way I can get rid of that noise is to subtract a frequency of 3 kilohertz, or the magnitude of 3 kilohertz. And I then come down and I do some what resolution I need, and then I end up with the thing called FFP equals et cetera, et cetera. And you can see that I got a FFP of 0.55. Well, you don't really want to do that every single time. So next, you could, but you don't want to, okay? What you want to do is to do it with a computational that does that substitution so that you end up with something that looks like that, right? When I do that, because I now divided it so that I have a ratio, and as I'm having kilohertz on the vertical axis, I have a ratio. That's nice because now I've reduced the number of models I need, okay? And I still got the same curve, but it's been shifted down to zero level. You can see the dotted line. That's where I shifted it. That's with the noise margin. So I've basically shifted the signature downward so that any noise perturbations in the absence of degradation doesn't give me a false indication of degradation. But I still have a noisy curve, and it's still curvilinear. Next. So I go back to that equation that we started with, and I go back with the P and the P, put it in that form, and do the substitution and solve for dP over P, and I end up with the red at the bottom there. And that's very nice because I've already converted my feature data into an FFP value. So now if I substitute that FFP value for every single data point I'm looking at and put it in that form, what have I accomplished? What have I done? I have taken the derivative of the original curve. And the derivative of a simple power function or an exponential function is a straight line. Next. And here are some examples. Up on the top are 3 different curves corresponding to 3 different failure modes. When I do the math that I've just done, which is to take the derivative of the original curve, look what I have at the bottom. I have converted that curvilinear input signal into a nice linear signal. And when I have a nice linear signal, it's much easier to say, if I'm here on this curve, how long will it take me to get to the next level of interest? Next. That DPS stands for Degradation Progression Signature. Okay? And it also works for exponential curve, not just power, but exponential. Those are 2 exponential curves, and down below is the equivalent degradation progression signature. And that data comes from a simple substitution into the solved model. Next. So we have identified, we in Ridgetop, and solved the equation models for 5 families of power functions and 2 families of exponential functions. These are not the only families that could in the real world, because of course the real world is in fact a Weibull distribution, exponent of an exponential. But what we have found is that taking the simple first order model is more than sufficient. There is still distortion, and that distortion is also a form of noise. Okay, and the key point here is that transforming feature data to FFP to DPS, we address the curvilinear issue, but it's still application dependent because I need a different signature model because of the difference in failure thresholds. And what I mean by that is a power supply used in a targeting system has a higher criteria than that exact same power supply being used to power, say, energize a bunny rabbit. Next. Okay, so I've done this, and I now want to convert my DPS into something that we call functional failure signature. And here's a characteristic of a functional failure signature. You'll see that on the vertical axis, it's all percent. And at 100%, that means that functional failure has occurred. We use the term functional failure as opposed to physical failure. It's sort of like a car tire. A car tire physically fails when it blows. But we never drive our car until the tire goes totally flat. We look at things, for example, like how much thread depth do I have? Is there any thread showing? Is there a bulge in my tire? So, and that's what you do with prognostic and electronic mechanical engineering. You look for something that indicates it's nearing the point where it's no longer capable of operating within specs. Next. Okay. What we have done to summarize the first part of this seminar is we've accounted for noise. We do that in addition to the standard filtering and signal shaping and smoothing. We subtract the noise margin. We shift that curve downward so we're not unduly bothered by noise. And then we've normalized the FD value by subtracting it to again shift the signal. Then we divide it by an appropriate divisor so that we keep the scale range within reason. And we've also get rid of the units of measure. So instead of kilohertz or milliwatts or ohms, all we have is a number, a ratio, and that's nice. And you choose your divisor so that under normal circumstances, if the signal below zero means it is perfectly good, and above 1 means it's failed. Okay, so then we convert the FFP to a degradation progression signature that basically linearizes it. Then we convert the DPS to a functional failure signature so that we can say failure always is at 100. Whenever the signal FFS is 100, it has functionally failed. If it's 0 or less, it is healthy. Next, good. So I'm going to go a little bit faster because a lot of it is just a summary. You start off with noise. You pick up, you identify what feature data you want, and you process that feature data, get it to an FFP, and that's familiar equation or model that you've seen. Next. So then your FFP is noisy, that your feature data. You can see that the FFP on the right side, it looks the same curve, but it has been shifted downward so that it's about a reference 0. And it has changed from kilohertz to a ratio. Next. Then we transform it into a data progression signature, which is basically, and you see there, it's basically a function of the FFPI. And that function, it depends upon what the original model was. But it's a derivative, and therefore it is more linear than the FFP, and you can see that, okay? That's actually, it looks the same, it's got the same kind of curve in it, but it's no longer totally curvilinear. Next. Okay, even so, what we've done by identifying the models that we have, instead of doing a rigorous derivation like we have done, use the solutions we already have, okay? And you pick out, like, for example, if I were to look at a ripple voltage, it's got a curve that looks like that, looks on the left-hand side. And after I condition it, it looks like that, and I do apply my, convert it to a functional failure progression signature. I've got the same thing where I've got a ratio on the vertical axis, and I've got the same looking curve. I've also mitigated noise by doing some data conditioning and smoothing. I can look at that curve and I say, well, it could be that it's a power curve, or it might be a exponential curve because they look sort of familiar. Well, if it's a power curve, that's the left-hand DPS. If it's an exponential curve, that's a solution for an exponential curve. Next. So then I run my experimental data through it, and depending upon what value, because I don't really know what the power value is, and you can see I have plotted for 4 values ranging from 1/4 to 2, and that's typically what you find, at least in electronics, as power values. And those are the resulting 4 curves. You can see that no matter what I do for the exponential solution, it's still curvilinear. So therefore, I can reject the exponential as being the solution and stick with the power. Next. And when I do that, I say, well, okay, let me try a half and a 1, and those are the 2 solutions for and n equals 1/2 and n equals 1, and there's a straight line there, and that's the ideal. So then I say, well, okay, let me try 0.4, and I do 0.4, and I plot it, and look at that. That's much more linear than what I started with. So what I have done, rather than going through a painful physics of failure analysis, deriving the equation and solving for it, I take Ridgetop's solution and I just play with it, okay? Next. So how do you know how accurate it is? Well, there's one way of doing it, and that's called functional failure signature nonlinearity. It's basically based upon determining the linearity of digital converters or analog converters. So what we have here, that the parameters of value is a time to failure. There's an ideal, so you can calculate what your ideal curve looks like. It should be a straight line transfer curve, and then you can calculate the deviation. Next. Okay, and there is the result when I apply that to the previous curve that I have. You can see that prior to degradation, it's obviously zero. It's always accurate. But once I go through, you can see that there's a variation of about plus or minus 10%. And that even before halfway, you can see at the very peak that it rapidly gets more and more accurate as you get closer and closer toward failure. So that's very good. The maximum deviation is less than 15%. That's actually, for real data, very good. Next. Okay, the prediction framework. The prediction framework now takes the functional failure signature, which has now been linearized, and it is going to produce what we call three prognostic pieces of information. One is state of health, which should go from 100% down to 0, remaining useful life, and prognostic horizon. Prognostic horizon is your current time plus your remaining useful life. Next. Okay. Ideally, your remaining useful life should start at, like, it would be ideal if for every single instance of something, we could accurately say, I know that once degradation starts, it will fail in 201 hours exactly. And if you can do that, then ideally you have a nice straight line progressing from 200 hours, and then 200 hours later is 0. Nice and ideal. Your prognostic horizon would be equal to 200, be a nice straight line. State of health should go progress from 100% to 0% at the same time. That's ideal. That's what you measure your accuracy against. Next. Even if your data is ideal, you can't predict exactly how long it's going to take for something to fail once degradation starts. So the prognostic engine, for example, if the input says this thing will last 300 hours or days after degradation begins, and let's say it actually fails in 200, the prognostic engine has to start from an error with 300, which is a 50% error, and as fast as it can, within reason, converge to the true solution. Same thing if it starts at 100 hours, that's again minus 50% error, and has to go ahead and increase its estimate so that it again converges to the time of failure. So there's more to a prediction engine than simply looking at a straight line and figuring out what's happening. It's got to do convergence, because it is unlikely the input is going to be perfectly linear. It's unlikely that it'll be noise and distortion free, and it is unlikely that the input is always exactly 100% accurate. Not going to happen. So our prediction engines, we use something called common-like filtering. Common-like filtering arose from estimating where a shell would hit. So it basically is estimating a flight, looking at the flight, for example, looking at your model and adjusting the model to match the flight, because it will always follow a certain curve. So if something is going faster or slower, you can adjust the curve to meet that. So that's common-like filtering. Look at the data, adapt the model, use the model to do the estimation. We also have to have a fast convergence algorithm. We use something like particle-like filtering. I say like because we treat a data point as a particle. A data point physically cannot change, make an abrupt change from, say, 0 to 100. Not going to happen. It takes a finite amount of time to get up to that speed. It's not going to all of a sudden rapidly change direction. Rapid changes are an artifact of the measuring system and your environment. We also do a random walk. It is unlikely that true degradation is going to go high, low, high, low, high, low, high, low. It actually goes low, a little bit higher, a little bit higher, a little bit higher. So it goes, it's like a random walk. It goes from low degradation to high degradation. We use trending, we use modeling, and we use machine learning. Next. So you could, I'm just going to go this real quickly because I've already talked about it. Common like filtering, fast convergence, particle filtering, random walk, trending. Okay, trending, for example, you can actually do in clip and clamp noise. Because if it's like say 100, and now the next data point is 150. Well, now and the data point after that is 110. Well, you need to clip that 150. It doesn't go from 100 to 150 back down to 105, for example. Real world doesn't work like that. Modeling, signature models, that we have dynamic builder model. We don't have static models. We use data spaces, so we break the path of a signature into multiple data spaces. We use machine learning. Next. Okay, this is a plot of a ideal, that's the dotted line, and this is a curve that you would obtain from ideal. And again, on the state of health, for example, even with ideal input, you can see that the state of health estimate is not exactly ideal. And that's because of the fact that we have to design the prediction engine to do fast convergence and to take into account for noise. And because of that, we can actually take ideal data and slightly perturb it, if you will. So you'll see some slight variations even when your input is ideal. And that's because your initial estimate is not going to be exactly correct. So it's either higher or lower than actual. Next. Okay, so the prediction engine, it does that, and then you have a performance validation network. We do that as basically a batch mode processing of data that has already been completed. And what we're looking for is how fast did we converge, how accurate was our estimates, etc. Next. And here are some examples, okay? And this is BD, means beginning of degradation. And you can see that we had actually predicted, we're now looking at accuracy. Our prediction was 50% higher, a little bit more than 50% too high. And you can see that in all of these examples that I used, I started degradation at 20. And you can see that we had converged from, on the 20th sample when degradation began, 2 samples later, we had converged from a 50% error to down to 25%. And then at 5 samples from the time that degradation began, we were within 5%. So, and failure end of life was, in this case here, at about 110. It was actually 117, or it varied depending upon the data between 100 and 120. This particular one looked like it failed at 105. So we have invented a term called convergence efficiency, and that is, given the maximum distance from the time of degradation when it began to the end of life, functional life, how fast were you able to converge to within 25% or 10%? And you can see that the efficiency here was 98% and 95%. Very good. Next. Okay. At Ridgetop, we have adopted what we call a 3-stage prognostic health monitoring system. The first stage is your hardware and your firmware, and that's what you attach to the node, a power supply, or you attach it to a leading edge of a wing if you're looking for stresses in the airfoil, for example. And then we have what we call a core. The core is the next 2 stages. One is the data processing stage, which conditions, fuses, transforms, that type of thing, smoothing. And the other one is the prognosing stage. And you can see that your condition-based data is very, very, very noisy. What you are actually looking at here is the phase currents from an electromechanical actuator. Those are actually 3 separate phase currents. We were able to look at that condition data, pick out a feature, process that feature, and produce what you see in the next 2 plots, which is remaining useful life, prognostic horizon, and state of health. And you can see that we rapidly converged within 25 and 10%, very, very fast, even though the data is very, very noisy. So the last part, which is the management part, is to take remaining useful life, prognostic horizon, state of health, and other information provided by our engine, and then figure out what to do with that data. Do I need to schedule maintenance? Do I need to reduce my power? Do I need to offload a load from this system to another system? That's very much application dependent. Next. Okay, we started off with that very noisy input signal that we had, and that's what's on the left-hand side. And now we're going to process it. And you can see that what it looks like on the FFP. The units of measure is now a ratio, but furthermore, we've applied some data smoothing so that the signature is a lot less noisy. There's still noise there, and it's curvilinear. And if you were to really study it, it's actually two parts. The first part of that curve is basically a linear progression. Then it becomes even more curvilinear. The linear part is because there's feedback in that power supply, and that feedback in the power supply, the loops, it's a double loop, has a tendency to want to offset a loss of capacitance. Next, we take the FFP and we transformed it using the models that we've developed, and you can see that we've actually, it looks more or less the same, it's got the same kind of shape to it, but it's much more linearized. We then convert that DPS, the degradation progressive signature, into a functional failure signature, and you can see it's now in percent, and you can see that there's a black and a red. The black is before we've adjusted the model. We did the transform, and then we do further smoothing. So you can see that we started off at a time that was very curvilinear, very noisy, and now it's much more smooth. Next. And we input that FFS into our prediction engine, and we end up with remaining useful life and prognostic and state of health. And you can see that you may say, wow, that looks rather noisy, but it's not really. Look at those horizontal lines correspond to 25% accuracy and 10% versus ideal. And you can see that, wow, we actually converge to much less than 25% inaccuracy very, very rapidly. And you can see the final plot on the far right, and you can see that we went from basically a 50% error to less than 25% very, very quickly. And then we did a little bit, or we got to within less than 10%, then we went above 10%, then we went down, and then we went below 10%, and then we finally remained within 10%. The key point here is that even with extremely noisy and nonlinear data, we got to within 10% accuracy in less than half the distance between onset of degradation and functional failure. Next, and that's with non-ideal. These are examples of ideal data, okay, simulation data. So you can see that the same model, the FD equals FD0, that's a power function. Depending upon your exponent, your power value, you can generate different curves, concave, both concave and convex. And when you transform it, the transforms are straight lines. Oh, that's really, really good. Next. And you can see that if my initial estimate is low, that it goes from low and then converges very rapidly to high, and then from high over to low. So slide 49 was from low to high, low to actual, and this slide is from high to actual. And you can see that our engine does a very, very good job. Next. Okay, this is again a different curve just to show that again it doesn't really matter what the underlying physical failure mode is. If you've done it right, or if you use our solutions, when you transform it to FFS, functional failure signature, it's a straight line. Next. And again, you'll see that we converge from a low estimate error to the actual very rapidly. Next. And with the same signature, whatever you got the same results, you would have got the same results from high to low. Okay, I managed to, even with the delays through the satellite, I apologize for having to talk a little bit fast at times, but I wanted to make sure that we finished on time and that there's sufficient time for questions. So, Wyatt, you can open it up for questions.
Yes, so thank you, Hoppy, for going through those slides and giving us a much better understanding on Ridgetop's approach to pH. Thank you for that. If anybody has any questions, definitely feel free to bring them up at this point.
Now, did you mention that there is a PDF of this webinar?
Yes, we will be able to send out that PDF after the webinar. So yes, we do have the PDF version available to be distributed.
Yeah, and we have the actual model solutions. We have Ridgetop have discussed those and made them available to through various conferences, and in a book that Ridgetop engineers has written and published by Wiley, and also so you can use this webinar and the conference papers and or the book and or contact us and work with us, and we will be more than happy to help you effect a solution for prognosing your system. It really is proper monitoring and management is really more than just attaching a sensor. There's all kinds of sensors out there in the world, and you can attach it to a noise and you say, well, it doesn't work. I can't predict when it's going to fail. And it's more than just putting the sensor on. You have to actually design how the sensor works. You have to gate the sensor so that it actually captures a feature of interest. You may have to actually sync your sensor with some sort of perturbation injection method so you can actually force a signature or feature to occur so that you can actually properly capture the feature of interest. Then you have to process that feature.
Okay, Hafi. So we do have a question from Jeff.
Okay.
Berg. And if anyone else has additional questions, feel free to put them in the chat and I'll bring them up for discussion. So, Hafi, can you comment on how uncertainties in the measurements and models are propagated into the decision-making parameters?
Say that first part one more time. How uncertainty?
Yeah, can you comment on how uncertainties in the measurements and models are propagated into the decision parameters?
Okay. There's a lot of uncertainty. Is mostly dealing with noise. Because that's what noise is. That's what uncertainty is. You're not sure whether what you're measuring is an accurate 100% representation of a change that's going to lead to failure. So you have to assume there's noise. And so what you do is you can do things like you capture some sample data, you do some simulations, and you say, okay, my noise, my uncertainty is say 10%. Well, that's 10% at the beginning, and that's 10% at the end. So that's a 20%. Well, if I use a common, a standard engineering of I'm going to build in a plus or minus 10%, you now say, well, okay, so my two 10% is now becomes 30% total. That means that 30% of your signal is useless to you because it's noisy. And you say, well, okay, I want my prediction to be within 10% accurate. Well, you can't because you already got 30% noise. So you can't be 10% accurate. So then you have to say, Well, okay, I have to reduce my uncertainty. And how do I do that? And that's where you have to say, well, okay, I need to put some bandpass filtering so I reduce high frequency and low frequency perturbations in my signal. I need to imply high sampling rate because that's also a means of filtering noise out. Uh, I need to increase my analog to digital conversion so that I don't lose important information. And so you have to look at your entire system until you reach to the point where you say, my noise is less than the accuracy I want. Because if your noise is greater than the accuracy level that you want, you can't meet your accuracy requirements unless you address the noise issue. So the biggest part of uncertainty is noise, and that's key. You need to reduce the noise to below the accuracy level you want. Everything else takes care of itself.
Hello, Hoppy. So thank you for answering that question. It looks like we have another question here where we're being asked if we have developed similar things, transformations, etc., for POF of different materials like electronics.
We've done some physical failure analysis. For example, we had a project where we were asked to come up with a method of determining whether or not a transmission cable inside of a submarine antenna mast was or was not damaged. And when we say damaged, we meant a kink or a crush. And therefore you can't measure that kind of damage. And even if you could measure it, it's impossible because one end of the cable is under the water in the submarine, and the other end of the cable is sticking up out of the water in the submarine, in the periscope or the mast that extends up above the water. So you can't really measure it directly. And so we were able to come up with an electronic means of detecting physical damage. We've also done something very similar with our fiber brag work that we've done, where we try to detect damage to wings, for etc. Did that answer that question?
Yeah, I think so. All right. So if there are any other questions, feel free to bring them up at this time.
Yeah, Wyatt or Hoffy, hi, Frank Myers here. I'm not sure what I need to do to ask a question, so I just opened the mic and jumped in if that's okay.
Yes, that's fine.
Okay.
Okay. You know, you go through a lot of things that you need to cover and all this stuff that you have to do. And if anybody that wants to use this as an application has your brain available to design all of that. I mean, do I understand? I mean, is this a process that can be used like universally? Uh, in simple terms, like a voltmeter or an oscilloscope, or is this something that you need to custom design for every particular application that might be necessary? And therefore, do you need not only to use the process but also use Huffy to design it for you?
And the answer is to the specific question, no. It is in fact or general, because as I alluded to in the webinar, you can actually do what I did or what we did at the very beginning, and that is to look at a particular failure mode, do the physical failure, do the failure mode effect analysis, and say, okay, for this particular failure of a capacitor in the output filter, the model is blah, 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 blah. And the solution for that model, for the derivative of it, is this. You could do that for every single instance, and that's long and laborious, and it's error prone. But once you have, like what we have, is a general solution for 5 power functions and 2 exponential functions, you can then take sample data, historical data, and/or simulation data, and say, okay, here's what the signal looks like under 0 degradation. 25% degradation, 50%, 75%. And you can plot a curve. Then you can match that curve and say, okay, of the curves that the Ridgetop already has solved, which of those curves does my curve match? And you pick that as a solution. Then you do what I did. You say, well, okay, I'm not sure whether it's this one or that one. So you take your simulation data, you run it through Ridgetop's algorithms, and you say, aha, it looks like the first model or the second model of your two that you chose is the one that linearizes the data the best. The hard part in prognostic, and we've solved the hard part for our customers, and that is how to analyze the data that is produced by the sensing system. What needs to be done, and what is really, to me now, the hard engineering part, is the sensing system. What sensor are you going to use to attach to what node to extract what kind of feature data, and how do I design my sampling system so that I can accurately capture the feature data each and every time without question? Because if you're just sampling and not syncing the sampling when the feature data occurs, then what you're really sampling is noise. You have to sync your sensing system to when exactly the perturbation occurs that you're interested in, be it the ringing response, be it the ripple frequency, be it some sort of shot noise or switching noise. You need to be able to sync your sensor to that feature. Then you need to be able to extract that feature and condition it. You need to be able to decide, do I need to do a DFT followed by an IFFT? Do I need to put on a Bessel function filter so I can shape the curve? What do I need? Okay, that's the hard part. And that requires a sensor engineer. The prognostics, the data signal processing, we have solutions on that, and those are general solutions. The last two stages that I showed you in the slide, that has worked for every single solution that we've come up with. We have not had to change that engine in years. We fine-tuned it to make it a little bit more accurate, but it is a general solution. The sensing system is not. The sensing system has to be matched to the system and the failure mode of interest.
Yeah, I'm not the sensor engineer, so that's why probably it sounds a lot more complicated than it would be for an expert in this matter like yourself. But thanks for the explanation. Thank you.
Yeah, and I would recommend that you obtain the book that we wrote. It's part of the Wiley series on reliability engineering. It's called Prognostics and Health Management, written by Doug Goodman, myself, and Dr. Ferenc Sidorowski. The ISBN number is 978-1-119-35665.
Isn't that on the website also, I thought?
I don't know. The Wiley has made an e-book. We have not put the book on the website because that would violate our contract obligations to Wiley. But okay. Wiley does have an e-book available.
Okay. Thanks very much.
Okay.
Okay. Are there any other questions? We could take a couple more here. Okay. If not, I'd like to thank everybody for participating in today's webinar. We really appreciate it. And if there are any questions that come up at a later time, definitely feel free to send out an email to myself or Hafi, and we'll get back to you as soon as we can. So without further ado, thank you everybody, and I hope you all have a great day.
Yeah. Thank you very much for attending and giving us the opportunity to basically show off what we've done. And it's been a pleasure working with you and talking to you. Bye.
Thanks. Bye-bye.